All right, now we are going to talk about a moving charged particle uniform electric field. And first we're going to review projectile motion. And then and then we're going to talk about the acceleration an object experience in a constant electric field. So, if we launch a particle in a gravitational field, okay, and here's our field of gravitation with all the little waving grains of gravity. Gravitation. Okay, never mind. All right, so we have an initial velocity, and we have a particle that gets launched up at an angle theta, and it travels like that. And at any particular moment, the acceleration acting on this particle yeah. Okay. At any particular moment, the acceleration acting on this particle is always the same, and it's always down. Okay, that's g. That's our acceleration due to gravity. G equals 9.8 newtons per kilogram, also known as meters per second squared. But a newton is a kilogram meter per second squared, and so this is a newton per kilogram, which is the value, which is the strength of the gravitational field when we are close to the Earth. If something is 2 kilograms, what force does it experience? 2 times this, right? 19.6 newtons. All right, so for every kilogram of mass that an object has near the surface of the Earth, it experiences a force of gravity of 9.8 newtons. All right. So, and then we have acceleration equals negative 9.8 meters per second squared. J hat, acceleration in the x direction, equals 0. And all of our kinematic equations come from here, and we can, yada, 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 blah, blah, blah. Okay. Now imagine we have a different situation. Imagine, if you will. A dimension not of time nor space, but of your imagination. We have 2 metallic charged plates. We've got a battery. Guys, knock it off. Okay. Along this charge plate over here, we have positive charges. Along this charge plate, we have negative charges, which means that we have an electric field that is pointing in this direction with the same strength no matter where we are in the field. Okay. This is our electric field. If we launch a charged particle, okay, a negatively charged particle in this case, and we give it an initial velocity in that direction, okay, what is its path of travel going to be like? Oh, I'm sorry, this is a positive charge here. Positively charged here. Okay. So, it's going to travel in exactly the same way because it's in a uniform electric field, just like our particle up here was in a uniform gravitational field. it will experience the same kind of force. Okay? Now, if this is a proton or some other similarly extremely small particle, we can neglect gravity. But let's say this has a mass of 10 grams. If it's a significant mass, then we cannot neglect gravity. Gravity is going to come into play. But in this case, no, we're shooting a proton in here. Okay, protons are so light that gravity is not going to be much of an effect if we give it a significant velocity. So, what is experience? Well, the electrical force it experiences equals the charge on the particle times the electric field. However, if this is the net force on the particle, it also equals the mass of the particle times its acceleration. Its acceleration then becomes so this now becomes our acceleration on our particle, and this we can use in all of your kinematic equations, and this is your, because the field is pointing straight down, your AY is now, Q naught E over M negative J hat, and then all of your kinematic equations come into play. Same thing. So you're going to have your V naught, V naught cosine theta, V naught sine theta for your X and Y components of your velocity. Everything else is the same. Okay, so we will be dealing with our kinematic equations even with charged particles. We're not done with those. That's it for moving particles.